Hello students, welcome to Math 3410 Differential Equations. In Lesson 1A, we cover nothing but preliminaries. So students with some strong background in calculus may wish to skip over this lesson entirely or any part of it. It's okay either way. Otherwise, let's begin. And we're going to begin with something trivial. Section 1, complex numbers, and that came from algebra and trigonometry. So I guess a lot of students will just skip section 1. That's okay. In that case, let's meet again in the next video. Here we go, complex numbers. The definition of complex number. Here we go. X plus yi, where x and y are real numbers, and I squared is -1. Here, x and y are called the real part, and y is called the imaginary. And I, the imaginary number. Okay, so much for the definition. Let's talk about some arithmetic. Addition and subtraction. Simply take the like terms together, and what do we get? We have x plus yi form again. Conclusion? Sum of any two complex numbers is again a complex number. Same for the subtraction. Take the like terms together, we get x plus yi form. So the difference of two complex numbers is again a complex number. How about multiplication? The same idea. Fold it out, take the like terms together, but remember I squared is -1. In the end, we get x plus yi form. Conclusion? Product of any two complex numbers is again a complex number. Finally, division. This is going to be a bit trickier. We have complex number over another complex number, but how do I simplify it? Well, let's pay attention to this red part. We strategically select a number and multiply the same number to both numerator and denominator. I can always do that. I can always multiply a non-zero number to numerator and denominator. Basically, it's multiplying by 1. So no change there. But why did I select a2 minus b2i, obtained by changing this plus sign to minus? If it is already minus, then I'll have to change it to plus. That thing is called the conjugate. We select the conjugate of the denominator. So change the sign of the imaginary part. So if I multiply by the conjugate, what happens? Let's go to the denominator, fold it out, and we have this part canceling each other out. And then I squared is -1. So in the end, what do we have? We have this expression, and that's real. So denominator is a real number now. How about the numerator? Well, just multiplication. Fold those out and take the like terms together. And what do you get? We have x plus yi form. So the conclusion again, the quotient of any two complex numbers is again a complex number. Of course, the denominator should not be 0. In short, we just proved that the set of complex numbers is closed under addition, subtraction, multiplication, and division by non-zero number. Here are some example problems copied from my college algebra notebook. Some more terminologies. Conjugate, simply change the sign of the imaginary part. Modulus, real part squared plus imaginary part squared. Add up and then take the square root. It's Pythagorean. It'll turn out that modulus, or the absolute value, is the distance from the origin. I'll show you in subsection 1.2. Next, let's go to properties of conjugate. Double conjugate, conjugate of the conjugate of the, we get the original. Basically, we are changing the sign twice. Plus becomes minus and then back to plus. Easy. Next, modulus of the conjugate is the same as the modulus of the original. Take the conjugate, then we have this minus y here, and take the modulus, then we have negative y squared. But then again, this is the same as just y squared. Therefore, we have the same expression as the original modulus. There goes the proof. Next, multiply the original and the conjugate, we get modulus squared. Simple deal. Just brute force computation, fold those out, and you're going to see the cancellation. And I squared is -1, so we have modulus squared, x squared plus y squared. By the way, we used this before, right here, when we did the division. This cancellation, and I squared -1, and then we got this real number here, which is actually the modulus squared. Next, D through G. These are talking about it does not matter whether you take the conjugate before or after all these algebraic manipulation. Addition, subtraction, multiplication, or division. How about the addition here? Addition first, and take the like terms together, and this plus becomes minus upon taking the conjugate, and then manipulate again, change the order, we have conjugate plus conjugate. How about the subtraction? Similar. We have this subtraction and take like terms together. We have minus and minus there, and this is plus, and take the conjugate. This plus becomes minus. Now, can you simplify and make it into this form by simply changing the order of subtractions? As a matter of fact, order of additions, adding the negative of something. Anyway, it's just an easy computation. Next, how about the multiplication? All right, multiply for those and take those like terms together, we get this. And this plus becomes minus upon taking the conjugate. And now, is this the same as the product of the conjugates? It's a little bit tricky to go forward, so it's better to go backward here. Start from the right hand side and fold those out and simplify. Do we actually get this? I'll leave the details to the students. It's not going to be difficult. Just take the like terms together, cancel out. Remember, I squared is -1, and you are going to get this. Finally, the division, the hardest of the bunch. Okay, this division, this quotient computation turns out to be like this, and that is exactly the same computation as we did over here. No, not this one. Here, this computation. Multiply by the conjugate of the denominator, simplify, and then separate. Except that here I'm using a's and b's, down here I'm using x's and y's. The same deal. And then take the conjugate. So this plus becomes minus. So far, so good. Now here's an ingenious step. Here, replace all the y's by negative y's. So this y1 and y2 there became -y1, -y2. Another negative, so they cancel out, and then just the same thing. Down here, y2 becomes -y2, but squared, so no change. y2 becomes -y2. Again, we square, so no change. How about this? y1 and y2, they become -y1, -y2. Now, these two contribute to the sign change. So this minus becomes plus. All right, we are done. What is this expression here? It is exactly the same expression as this expression down here, except all the y's are negative. So we have to have the same quotient, except the y's are negative, as you see here. So we have the quotient of the conjugates. The detail is left to the students. In the end, it does not matter which arithmetic we do, addition, subtraction, multiplication, or division. We can take the conjugate either before or after. Doesn't matter, no change. Finally, conjugate of the real number is itself, and the proof is really easy. X plus 0i becoming x minus 0i because we are changing the sign of the imaginary part. Real part stays the same. How about the next topic? Complex roots of quadratic equation. Okay, quadratic formula. Duh, everybody knows this. Everybody should remember this. Okay, all right. Next, the fundamental theorem of algebra. Okay, this is significant. It can get real deep real quickly. But in college algebra level, just stick to this. Every complex polynomial can be factored completely in linear factors, as we see down here. Here, S1, S2, S3, those do not have to be distinct. So if you have the same zero repeating, then we're going to have just a multiple zero. That's about it. In any case, any polynomial in complex number system can be completely factored into linear factors, first degree factors in complex number system. That's the fundamental theorem of algebra. As for the proof, we cannot do it here. It's way too complicated for Math 3410 level. And the right course is going to be functions of complex variables. Functions of a complex variables, I think. And I forgot the course number, 45 something. I taught it once here in UNT Dallas and twice before coming to UNT Dallas. And each time I taught that course, I covered the fundamental theorem of algebra there. Maybe I'll do it someday. At this moment, let's just leave it at that and move to the next subsection. Complex plane, which was covered from trigonometry. Okay, a complex plane, x plus yi corresponds to x comma y, as we see in this kind of visualization. First example, 2 plus I, that corresponds to this blue point here, 2 comma 1, and the red point down here is the conjugate, 2 minus I. How about second example here, 3/5 minus 4/5 I, that corresponds to this blue point down here. And then this red point up here is the conjugate. How about this example, -3 plus 2i, that corresponds to this blue point here, top left-hand side, and here, down here, that's the conjugate. Symmetric with respect to the x-axis. Oh, by the way, what about modulus? By Pythagorean law, that is a distance from the origin. Hypotenuse, distant from the origin. All right. Now that we have complex plane, we can do xy plane, but also we can do polar coordinate. As you can see from this kind of visualization. Okay, theta is 1.628 pi or something like that. Okay, all right. And then r, x squared plus y squared, square root. That's Pythagorean, so that's the distance from the origin. That's the modulus. This program is randomized, so I'm going to get different value each time I run. Okay, this time, angle is measured clockwise, so we have negative theta. Theta is negative. Do you see? Negative 0.57 pi. That's because we are measuring clockwise. Counterclockwise is the positive direction. Now let's look at this triangle. In first quadrant, it's easiest to see. What is x and y? X is horizontal and y is vertical. And horizontal over hypotenuse is cosine, so x is arc cosine of theta. And vertical over hypotenuse is sine, so y is arc sine of theta. Therefore, x plus yi is the same as arc cosine of theta plus I times arc sine of theta. Factoring r out, the modulus, and what do we have? Cosine of theta plus I sine of theta. This expression here is called the polar expression of the complex number. And it turns out that this expression here, cosine of theta plus I sine of theta, is the same as exponential of I theta, e to the I theta power. Now, this final conversion here was not covered in Math 1600 trigonometry. It's covered in Calculus 2. I usually do it there. Some students may not have seen this in Calc 2. It's okay, we're going to cover it in the next section. Okay, what kind of arithmetic can we do on the polar coordinate? Here's the addition. Here's the multiplication, excuse me. Multiply two complex numbers on the polar form. So multiply the moduli r1 times r2, and that's easy. And how about this angle part? Cosine of theta 1 plus sine of theta 1 times this. It turns out we're adding up the angles. The proof? Well, here we go. We have to use the sum and difference identity of sine and cosine. And that's the way we did in Math 1600 trigonometry. But if you use the exponential expression, then it's just trivial expression. It's just an exponent rule because we have the same base e, so we just add up the power. How about division? Again, the similar deal. Divide the moduli and subtract the angles. How about the proof? We can prove it like this. And again, we are using the sum and difference identity. But if you go beyond 1600 trigonometry and embrace the arguments from Calculus 2 and express those in exponential form, then this is much easier. Nothing more than exponential because we have the same base e, so we simply subtract the powers. Now let's go back to this multiplication again. What if you multiply the same thing over and over again? We're going to get the nth power. And modulus part is multiplying r over and over again, so r to the nth power. How about the angle part? We are adding up the same thing over and over again. So we have n times theta. That's called de Moivre's theorem. It's a repeated application of this rule. But if you use sine and cosine, and that becomes rather tough with those sum and difference identities. But if you use the exponential expression, that's really easy. It is nothing more than just the exponent rule. So this calculus 2 expression of complex number, exponential expression, is really powerful and useful. Applications of de Moivre's theorem. Okay, I got these from my trigonometry notebook. If you have time, you can read about it. And that's where I'm going to stop. As for the exponential expression of trigonometry, we're going to talk about it in the second section when we talk about those preliminaries that came from Calculus 1 and 2.